Welcome to this ECE 201 lesson titled Writing Node Voltage Equations from Kirchhoff's Current Law. We will learn this technique by example using the circuit that we see here. Suppose our ultimate aim is to determine the power associated with each of the 6 circuit elements. We can use the equation power equals current times voltage, P equals I times V. But how do we get the I? How do we get the V? One way, of course, would be to write the connection constraints, that is, all the independent KCL and independent Kirchhoff voltage law equations, and all the element constraint equations, Ohm's law, and so forth. This would yield 12 equations for 12 unknowns. But a rather more elegant method is node voltage analysis. This is also a systematic step-by-step approach, but involves a simpler set of equations. Let's demonstrate how it works. The first step in node voltage analysis is to choose or identify one of the nodes as a reference node. Then voltages at all other nodes in the circuit will be with respect to this reference point. Recall that voltage is an across variable. We speak of the voltage across 2 points in the circuit. Designate this reference node with a ground or reference node symbol. As we see here in this example, we've chosen the bottom node in the circuit. Now, a node is defined as a juncture between 2 or more branches of a circuit, and it includes all the zero resistance wire between connection points too. So our reference node includes all the circuit within the dotted red box that we see on this screen. Having identified a reference node, the next step is to label all the other nodes, either with an unknown node voltage to be solved for, or if we can see the value of the node voltage by inspection, simply label it with that value. In this circuit, the junction point between the 10-volt voltage source and the adjacent 10-ohm resistor corresponds to a known voltage. We see a 10-volt voltage source connected between that node and the reference node, so we can simply label it with 10 volts. But the other 2 nodes are labeled with V sub A and V sub B, and we will solve for those. The third step is to write KCL at each node for which we have an unknown node voltage. In writing KCL, express the currents using element constraints and the node voltages. As a specific example of expressing a current using element constraints and node voltages, consider the current labeled I sub 1 here. The elements are resistors, so the element constraint or the element equation is simply Ohm's law, and I sub 1 is equal to V sub 1 divided by R. And please note the use of passive sign notation here. So the resistor voltage V sub 1 is expressed in terms of the node voltages as V sub A minus 10 volts. Continuing with Kirchhoff's current law at this node, we identify 3 currents, I sub 1, I sub 2, and I sub 3. And one way to write KCL is to say that the sum of these currents with reference arrows pointing away from the node is 0. In this case, I sub 1 plus I sub 2 plus I sub 3 is equal to 0. Now I sub 2 is equal to V sub A over 10 ohms. And I sub 3 is the quantity VA minus VB divided by 10 ohms. This provides us with a way of writing KCL in terms of node voltages. The fourth step is to collect terms for the KCL equation. So we have V sub A times 0.3 inverse ohms or Siemens minus VB times 0.1 Siemens minus 10 volts over 10 ohms is equal to 0. Of course, 10 volts over 10 ohms is 1 amp. If we take this to the right-hand side, KCL at this node is now expressed as 0.3 Siemens times VA minus 0.1 Siemens times VB is equal to 1 ampere. This is one equation with 2 unknowns, but fortunately we still have another node to look at. We continue our process then by applying steps 3 and 4 to the remaining nodes. In this case, that is the remaining node singular, node B. The algebraic sum of the currents leaving node B is quantity V sub B minus VA over 10 ohms plus V sub B over 10 ohms minus the 1 amp from the current source. Remember that if there is plus 1 ampere flowing from bottom to top, there is minus 1 ampere flowing from top to bottom. This results in a Kirchhoff's current law expression at node B as minus 0.1 Siemens times V sub A plus 0.2 Siemens times V sub B equaling 1 ampere. So the procedure just outlined produces equations that can be readily solved for the node voltages. In this case, one finds that V sub A equals 6 volts, V sub B equals 8 volts. Certainly simpler than solving for 12 equations for 12 unknowns, but on the other hand, we only know the node voltages. How does that help us in our original goal of finding the power associated with each element? Well, the beauty of node voltage analysis is that once you know the node voltages, you can determine all the voltage and current parameters in the circuit. It is as if the knot now just easily unravels. It's especially straightforward to find the element voltages once we have the node voltage values. For example, the 10 ohm resistor on the left-hand side of the circuit we see has 4 volts across it. It's the node voltage at the element's plus polarity reference mark minus the node voltage at the element's negative polarity reference mark. Continuing for the voltages associated with the rest of the circuit elements, the results are shown here. Take a moment to look at them. Perhaps I should mention that in some cases, for example, the current source, the node voltage associated with the minus polarity reference mark is 0 because it's the reference node. So for the current source, a voltage of 8 volts is indicated. In any case, we see that once you have the node voltages, getting the element voltages, simply subtract 2 numbers. Once we have the resistor voltages, we use Ohm's law to obtain the resistor currents. For the 10 ohm resistor on the left-hand side of the circuit, for example, the current equals 4 volts divided by 10 ohms, or 400 milliamps. Once again, note the use of passive sign notation, please. Continuing, we want the currents associated with the energy sources. For the 10-volt source, Kirchhoff's current law can be used to determine its current, and with an eye toward calculating power, we continue to use passive sign notation with that current reference arrow pointing into the voltage polarity plus reference mark. Likewise for the current source. So the power associated with the 10-volt source, power equals I times V, is minus 4 watts. The minus sign indicates to us that the source is generating power or delivering power to the rest of the circuit. The power associated with the adjacent 10 ohm resistor, I times V, is plus 1.6 watt. The plus sign indicates the resistor is dissipating power or absorbing power. Well, our goal was to use node voltage analysis to find the power associated with each circuit element in this example circuit. And we can now proceed to use power equals I times V to complete that process. The results are shown here. Note that the sum of the generated power, 12 watts, equals the sum of the absorbed power, as it must. That's always a consistency check that one can carry out. This will conclude our ECE 201 lesson titled Writing Node Voltage Equations from Kirchhoff's Current Law. Thank you for watching. Let's just briefly summarize the process. Step 1, identify a reference node. Step 2, label all the other nodes. Step 3, write KCL at those nodes expressing currents in terms of the node voltages. And step 4, collect the equation terms in terms of the node voltages, solve for them. After we've got the node voltages, we can readily obtain all the other circuit parameters.